Hello everyone, in this video I'll be talking about fourth order RK4 method or RK2. In the last video we covered RK2. In this section we're going to talk about RK4, which is very similar to RK2. The only thing is the accuracy of RK4 is RK4 is actually fourth order, RK2 is second order, and that's what this 2 and 4 actually comes from. So that means if you do the Taylor series and the approximation, you would see that the error that you get is on the order of h squared for RK2, and the order of the error is going to be proportional to h to the fourth power for RK4. Okay, all right, so let's jump into RK4. So in RK4, we again look at our generic differential equations. Let's say dy dt is equal to f of y and t, pretty much like what we did in equation 5.19. So this is the general form of the equation I'm going to solve, right? And then, so we do it in basically 4 steps. In step 1, we calculate something called k1, which we evaluate function at point tn and yn. Let's say that's the current point, right? And h is dt. Then we evaluate k2, which is h times the function. F is the right-hand side of our differential equation, right? So f is always the right-hand side. So you're going to evaluate the f at yn and half of k1 and tn plus half of h. So we evaluate the function at this new point, tn and tn plus h over 2 and yn plus k1 over 2. We call it k2. Then we evaluate f again at another new point, which is y plus k2 over 2 and t plus h over 2 again. And so you see that the y values change, but the t values are almost, well, they're identical. Okay, so that's going to be k3. And then k4 is going to be the function f evaluated at y plus k3, right? So it's y plus k3. And then t plus h, well, tn plus h. Tn as the time value, or xn, you can call it independent variable. So independent variable at the current point. Okay, and then we can calculate yn plus 1. So after 4 steps, we can calculate yn plus 1, which is the current y plus 1/6 of k1 plus 2 times k2 plus 2 times k3 plus k4. So it's like weighted average of the k's. Okay, this is proven to be fourth order. This is the most accurate method that we covered in this class. Again, that means if you lower your h by a factor of 10, your error goes down by a factor of 10 to the fourth power, which means 10,000. So that means by lowering h, your error goes down very, very rapidly. So contrast this to forward backward Euler, which were OH. Trapezoidal method was OH squared, and RK2 again was OH squared, but RK4 is OH to the fourth power. Okay, so let's look at the same example we did with RK2. Now this time we're going to do with RK4. That is example 5.4. It's a reaction. It's a first order reaction, where we call V over F, we call it as tau. Okay, so dc dt is equal to minus c over tau. So here's the exact solution. You can easily compare that with the exact solution. Okay, so here's example 5.4, which we did using RK2 before. We're going to go to RK4. All of these are already on Blackboard, so you can go and download the script and play with it. It's on script tab of Blackboard. Okay, so now we're going to do this. dt is 0.1, let's say for now. Tau is 0.5, similar to RK2. So here's the tau for RK2, right? I'm using the same dt and tau. Okay, again, tau is V over F. Okay, and V over F are here, according to equation 5.25. Okay. So here's the time vector from 0 to 1 with the increment of 0.1. This is no problem. Then before we calculate RK4, we have to calculate the 4k values. So k1, k2, k3, k4. And then we get the weighted average, which is 1/6 times, the weighted average of the k's according to this equation right here. So this is also no problem. The only issue is actually I have to calculate the k's, and then that's it. So because RK4 is 1/6 of, according to the equation, 1/6 of K1 plus 2K2, 2K3, and plus K4, and that's what I have here, plus the accumulation term, because we always calculate the next y value with respect to the previous one, right? So that's the previous one, yn, or cn plus the weighted average of the k's. Okay, so this is also no problem. Let's calculate first the K1. Okay, K1 is the current y, so look at that. So K1 is h, which is dt, or delta t, times the function evaluated at the current point. And so dt is 0.1, so that's why I have the blue cell, times this thing is the function evaluated at the current point. So what is the function? The function is the right-hand side of my differential equation. What is the right-hand side of the differential equation? Well, 5.4. The right-hand side is c divided by tau. So let me write it here. So we remember that every time we get back to this equation. So this equation is simplified to dc dt is equal to minus c over tau, where tau is v over f. So every time I want to calculate, that's a little f, it's going to be minus c over tau. Which c? The current c. Okay, let's go back here. What is K1? Minus c, which is B3, the current value, right? That's B3, it's supposed to be black or whatever, and that's greenish. And then divide by tau, which is frozen, and that is the purple cell. Okay, so the parentheses is the f. Okay, let's go to K2. K2 is going to be h again, which is B1, the blue cell, times minus, and then now we have to evaluate the function. So this is the tricky part of it. You have to evaluate the same function at yn plus half of K1, right? So here it is. This is yn, which is B3, plus half of K1, which is the purple cell. So that goes into the c value. Which c value? The c value in the function f. Remember function f? That was minus c over tau. Now this c is going to be the current c plus K1 over 2. And that's what I have here. So it's this current c plus K1 over 2, and then the whole thing divided by tau, which is the brown cell. Okay, that's K2. That's the K3. Again, it's h, which is dt, times minus, and then we have to evaluate the function at y plus half of K2. So here's the y, the current concentration, the green cell right here, plus half of K2, which is D3, the purple cell. And then the whole thing divided by tau. Okay? And then K4 is again h, so get back to here. K4 is h times f at yn plus K3. So here is minus, and then the current value plus K3, the purple cell. And then the whole thing divided by tau again. So that's it. If you do these 4 cells properly, the rest is just pretty easy, just drag down. Okay? The exact solution, we know it, so we just manually hard-code it in here. Okay? So that is h times exponential of minus t divided by tau. Okay, so t is 8.3, tau is purple cell. That's the exact solution, and here's the Euler method. You want to just compare with the Euler method if you remember. So initial condition is 1, no problem here. For the second cell in Euler method, that's going to be yn, right? So according to Euler's method, yn plus 1 is equal to yn plus dt times f. So here's dt, right? So that's b1, and then times the function evaluated the current, and the current y value, which is minus 1, c, which is h3, right? That's the current y value, h3 divided by tau. Okay, so that is the Euler method. The rest is, I can assure you that I can clear this up. I can clear this up, and I can clear this up. So that's what we did so far. So we calculated yn plus 1 using RK4, which is the weighted average of the k's, plus yn, right? Again, go back to Euler method. So the current y plus the weighted average of the k's, and that's what I have here, right? And then that's the Euler method we did. So we're going to drag down, I have to do this first. Double click on the lower right corner, highlight these four, double click on the lower right corner, highlight this, double click on lower right, highlight this, double click on the lower right. This is it. So we can go and plot. So red is the Euler method, which is first order approximation, and that's the least accurate among these. The exact solution is the solution, which we pretend that we don't know, but we just want to have a comparison here. That's what we calculated. Okay, so this is the Euler method. It should be less accurate than RK4, which means RK4 should be closer to the exact solution. All right, so that's the exact solution. Ready to see that? The exact solution is brownish, and then RK4 is bluish or greenish, and it's almost indistinguishable. Right, so you don't see, I mean, exact and RK4 are very close. Euler method is a bit off. And we expect that because Euler method's fourth order, it's first order, and RK4 is fourth order. It means the error actually is smaller. For a small delta H, which we picked up here, 0.1, the error in RK4 should be smaller, right? So that's why it's closer to the exact solution. Okay, so that was RK4. In the next video, we're going to look at how we can do, so far we only focused on one specific equation, let's say this, right? Or in a general form, the equation we look at was dy dt is a function of y and t, just one equation. In the next video, we're going to talk about how we can solve a system like we have multiple equations, right? So that's what we deal with system of equations. So like we're going to have dy1 dt, dy2 dt, all the way to dy(n) dt. Like we have n equations with their right-hand side. And their right-hand side is a function of those n y's and the t. So the independent variable and n dependent variable. For each, we have one condition. You can think of those initial conditions. So let's say we have n equations, n initial conditions. We're going to solve all differential equations simultaneously. All right. Okay, so thanks so much. Stay tuned for the next video on solving systems of ODE or IPEs.